Now we have an important concept called an orthogonal projection. We have a vector v, and we want to project a vector u onto v. So what we do is drop a perpendicular straight down to v from the tip of u. The projection of u onto v is the vector starting at the tip, the tail of v, going to where that projection ends. So this would be the vector projection u onto v. Now there's two things about this vector. One is the length of this vector is just the side length of this right triangle. The other is that this vector is going in the same direction as the vector v. Now, if we want to determine the length of this vector, we can do so by finding the length of the side of the right triangle. So if this is an angle theta between u and v, we know that cosine of theta would be equal to the adjacent side, which is that projection of u onto v's length, over the magnitude of the hypotenuse, which is the magnitude of u. That means that the magnitude of the projection of u onto v is equal to the magnitude of u times cosine of theta. Now, that's the length of that projection. If we want to actually find that vector, what we want is to find a multiple of the vector v. I can find a multiple of v that has length, the magnitude of the projection of u onto v, by forming a unit vector, which is v over the magnitude of v, and then multiplying it by the length of that projection, which is the magnitude of u times cosine of theta. So this is the length of the projection, and this is just the unit vector going in the same direction as v. Now there's several ways to represent this vector. We could just refer to the length of this vector, which is the magnitude of u cosine of theta, by a different term, and we'll call that the scale of u onto v. So that is just the length of the projection. And then that length times that unit vector going in the same direction as v. But we also know that u dot v is equal to the magnitude of u times the magnitude of v times cosine of theta. That means that the magnitude of u cosine theta is equal to u dot v over the magnitude of v. Well, another way to write this, think about v dot v. V dot v is just the magnitude of v squared. So if I want to take, I have u dot v over the magnitude of v, and then I still have times v over the magnitude of v. If I combine these two magnitudes of v, the magnitude of v times itself is just the dot product. So I can rewrite this as u dot v over v dot v, and then just times the vector v. Now, two ways to represent this scale would be, it's just the magnitude of u times cosine of theta, which is what we found that magnitude of that projection to be, or just u dot v over the magnitude of v, which is what we had right here. So different ways to represent the same thing. Scale of u onto v is the length of that projection. The projection itself is that length times the unit vector going in that same direction. So now let's find the projection in the scale of u onto v. Let's find the scale of u onto v first. That's just u dot v over the magnitude of v. U dot v will be 4 times 3 is 12 plus 4, and the magnitude of v will be the square root of 9 plus 16. So 16 over 5. Now we can use that to get the projection. Remember, the projection is just the scale of u onto v times v over the magnitude of v, which is just that unit vector in the direction of v. This will be 16 fifths. And now let's find that unit vector. V is 3, 4. The magnitude of v is just 5. So we have 16 over 25 times the vector 3, 4, which could be rewritten then as 48 over 25 and 64 over 25. Now let's see what this is geometrically. The vector 4, 1 and we'll project that to the vector 3, 4. To project u onto v, we'll drop a perpendicular straight down to v, and that projection will be the vector starting at the origin and going to where that projection hits. And now 48 over 25, that's around 2, comma, and about 2.5. And that's pretty good, pretty accurate graph. Okay, now let's do it for the second problem here, but I'm going to go ahead and find the projection of u onto v first, just individually. We had a formula. The projection of u onto v could be found using this formula. Since I don't have the angle, there was no reason to use this form, and this one requires me to find that scale first, so I'm just going to use this form. So u dot v over v dot v times the vector v. U dot v will be -4 plus 3 over v dot v, which is 1 plus 1. And then the vector v, so we have -1/2 times the vector 1, -1, which would be the vector -1/2, +1/2. Now the scale of u onto v. Again, I don't have an angle, so I will use u dot v over the magnitude of v. I could just find the magnitude of the projection that I just calculated also. Okay, u dot v will be -1. The magnitude of v will be the square root of 2, and that will be our scale of u onto v. Now let's look at it geometrically. We have the vector -4, -3, and then 1, -1. Now when we project the U onto the V, we need to extend V out in the opposite direction. The perpendicular here would actually fall on that side in the opposite direction. So this is the projection. If you look at the point that the actual vector that we found, the component form, it's negative 1/2, 1/2, which is pretty close. And the length of that vector is negative 1 over the square root of 2.